Hey, welcome back, neighbors. Today we're continuing on with our ABS sensor diagnostic tool build. Now, I've gotten pretty far since the last video in that I wired up our transistor and our switch to the flashlight here. Now, most important thing now is to be able to test it in the lab. So let's get into that. So basically, what we have here is our logical diagram again, basically how this thing works. But in order to test all our good work, we have to be able to simulate a sensor signal. Now you may be wondering, why am I simulating this? Well, in designing things, we need to be able to do things in the lab. I obviously can't bring in an ABS sensor and a wheel and a car into the lab to do that. So, and then also be making changes on the fly. So it's much easier if we create a simulator, all right? Something that simulates this signal. And that's where we go into this. Now, while we can build circuits with timers and oscillators to actually simulate the signal, I thought, why not give an opportunity to introduce microcontrollers to you guys. So for those of you who are brand new who don't know what microcontrollers are, basically are computers, entire computers on a single board. Okay, basically what this does is allows you to program functions onto this chip here without needing to build complicated circuits around it. So how are microcontrollers relevant to our work here today with the ABS sensor? Well, unlike a PC or a laptop computer, this is a relatively very simple device, a really simple computer. It allows you to, just out of the box, allows you to control each one of these little pins here and the holes here are connectors. Okay, if you can see like this, right? And they're labeled like from 13 to 0 and whatnot. But what these pins are is a way for you to interact with the world in a very simple way. We can individually control. We can write code and programs and program this chip to individually control each pin on this board here. There are many pins to use. And this is a perfect opportunity to program something to simulate the ABS sensor signal in the lab condition, right? And this is inherently very easy for this kind of a architecture computer. Now, if you were to do it on a laptop, while it probably is possible, you would need additional hardware on top of that to control the ports effectively, and you'd have to write drivers for it and stuff, and that would be pretty hard. Whereas you can write simple code, probably I will show you in less than 10 lines of code, I can get this to simulate an ABS sensor signal. Okay, so let's get into that. How do we program one of these? So we're going to put away this for a moment and open up our laptop. It doesn't have to be an Apple. Log in here. Now, let me zoom in a bit. Now, basically, the package I'm using, because this is basically a Arduino Uno board that we have here, right? To program it, we go into the Arduino IDE, okay, and that's downloadable on the Arduino site for free. It doesn't cost anything. So this is the interface for it. Now this is where we write the code. This is called a sketch, and this is how the logic is set up. So at the top here we have some constants. Setting up the output pin. This is just declaring that the output pin is pin number 12. I choose that arbitrarily, but the reason why we use pin 12 is because it actually is it is one of the digital output pins. There is some documentation on the Arduino site that tells you which pins can be used for what purpose, right? So every sketch has a setup block in the code which executes before the main body of the logic, which is the main body of the logic in the loop here. So as I said, this is literally 15 lines of code minus the spaces in here, which I can now make to simulate a ABS sensor signal, okay? So basically what this is setting the pin mode. As soon as this thing starts, it's going to set the pin mode to output. So pins are bidirectional. They could be input or output, but we want to set it to an output mode because we are actually outputting a signal here. Now this main loop, after the setup is finished, the main loop basically said, well, I'm going to write a digital high to the output pin. And then I'm going to delay that for 100 milliseconds, as said here. So the pin will stay high for 100 milliseconds. Immediately after that, we're going to write a low to the same pin. So for high it means a 5-volt signal, a VCC signal. Low, it means a ground signal. So it's going to go infinitely in this loop over and over again, writing a high, which is a 5 volts, onto the pin, and wait for 100 milliseconds, and then I'm going to flip it to a low to write a 0 volts onto that pin, and have that hold for 900 milliseconds. Okay, so all in all, it's basically a 1 hertz signal. So every 1 second, this is the duration of the period of the signal is 1 second. But within that 1 second, I'm spending 10% of the time in the high state, 90% of the time in the low state. So if you know anything about pulse width modulation, this is called a 10% duty cycle, right, of a frequency of 1 hertz. So this is what it does. Now, in order to get this code to run, you need to load it onto this microcontroller. And the way that works is that it comes with a USB cable, and the other end is on this side here. You're just going to plug it into your machine here, into any USB port on your computer. Okay, give me a second here. And what you have is, now you can see some lights light up, meaning that the board is given power, right? There's an on LED here. So once that's connected, we can go into our tools here or the sketch. We can say upload. Now I'm going to zoom out here, and you're going to see for a second things that come on the screen. So we're going to click upload, and you see at the bottom pane here that the sketch uses 2% of the available storage on the machine, and it's basically done writing it. Okay, so we zoom out. So now the program is on the board, and it is executing. And if we were to check pin 12, you will see that it is generating a signal that has the desired frequency and duty cycle that we've set. So now we're going to test it. I've hooked up our microcontroller to the USB, and all it takes is a USB port to power this thing up. So the power and also the programmer all come through the USB. But right now, after it's been programmed, any USB port will power this thing up. And that's where the supply power comes. So now we can use the oscilloscope. We can check the output signal on this pin 12 that we programmed versus the ground pin here. Okay, so let's just hook it up. Let's see what's on our oscilloscope. We're going to use the green channel 1. Ground, go, and now put it there. And as you can see, the signal is coming through. It's at 5 volts, and you can see that it's at a certain, the period and the frequency is right. Okay, you can see the frequency down here on the mouse here. I can show you, point to it. It's 0.99 hertz, so that's just about right. This is not an ultra precise oscilloscope, and nor is it writing the code this way to do a pulse width modulation signal is not entirely 100% accurate. There are other better ways to do it, but we've done this in this case for this simplicity. Okay, because the native pulse width modulation that comes off of the microcontroller with this setup would be way too fast for our purposes. Okay, the oscilloscope can capture it, but it'll be too fast for the ABS sensor signal. Okay, so it is working, but you notice there's a problem. The peak is about over 5 volts, just over 5. What we need to do is cut this voltage down, because the ABS sensor is supposed to be only 0.5 peak to peak. In an AC signal, it can go from positive 0.25 to negative 0.25. So we can't generate a negative signal on this one, but what we can do is chop this signal down to 0.25 volts using a voltage divider. So I have rigged up something like this. Okay, it's just a series of resistors in the right proportion to get it down to well, I hope it focused, to get it down to 0.25 volts. So let's hook that up and see what it gives us. So this is how I hooked it up now. Okay, so the output pin 12 is hooked up on these resistors. Hope this focus. And I'm gonna take the output voltage from the center here, right here. Okay, so I'm gonna put this down. I'm gonna put my oscilloscope probe onto the center, and you should see that it's gonna be 0.25 volts. Okay. So you can see down here that the signal is down here now. You see these little tiny bumps? Same signal as before, except it's chopped down to a very low point. So let's measure that. 440 millivolts, 360, 20, 280, something like that, right? If we go even lower, we can change the scale on the oscilloscope. We can change it to 1 volt per division. Okay. So you can see it's pretty accurate now, right? 300 millivolts, something like 280 there with a little noise. Let's go even lower. Let's go to 200 millivolts per division. Okay, now we can see it clear. So I'll move this up right at the top of that. Okay, so now you can see, right? 228. So it's pretty close to our estimate, and this should be good to use as our signal simulation for our signal. So now all we got to do is hook it up to our setup and put that signal into the into our device to test it out. So I'm going to show you how I wire this up. Now, I'm not going to lie, I did this off camera, and our tuning for our transistor, our biasing of our transistor base was a little bit off. Everything is a little bit off sometimes when we do these things because the resistors, we can calculate in math, exactly how much resistance we need on the resistors for the biasing and stuff. But the reality is you got to use resistors that are available, right? So you have to make adjustments because they're just resistors come in different steps, different levels, right? There can be 1K resistors, 1K, 0.2, there could be 5.1, 5.6, 10K, etc. They don't make every resistor in every single size. So you got to make the best matches you can. And the first couple of times I tuned this, it probably took me about half an hour to get this, is just the right tuning, just the right amount of biasing to get this thing to work. Okay, but let's show you how this is hooked up. Okay, first of all, what we need to connect is the grounds. Okay, so I have this wire temporarily tied onto here, not very nice, but we've got to connect it to the ground of the microcontroller right here. Right, and the other point is the signal wire from the microcontroller, this white one here, that needs to go into the base or the gate of the of our transistor, and it doesn't go directly to the base. It goes into the. I've added a capacitor right here, as you can see. Now, what the capacitor does is a very necessary thing. It prevents the DC voltage coming from the battery, from this our flashlight here, from going into the signal, okay? Because that can alter the signal. We don't want that. So basically, when capacitors are wired in series, it's called AC coupling. It's used to block DC signals, but at the same time let AC signals flow through. The size of the capacitor you choose has a bearing on what frequencies of the AC signals can be let through. So if you put, in general, a larger capacitor means a lower frequency signal will be passed through. If you put and higher frequency will be cut out, right? So you gotta tune this one. So realistically, I've chosen a size, and we can get into another video about how to choose size of capacitors. There's a little bit of math involved in figuring that one out. But for this purpose, I've chosen a capacitor that would most likely be in the right range where if we're testing an ABS sensor, it would be at the right frequency. Because as we said, I think it's going to be around 44 teeth in the ring for the wheel bearing, the reluctor ring. There should be only 44 teeth or something like that. And we spin it at a good speed that you can do with your hands, probably around 20 hertz, right? 20 times a second, you would get that. So I've tuned this circuit for that purpose. Now, again, we're going to go to connecting it. So let's connect it to the base. Here we go. Join it here. It's hard to do because I'm doing it behind the camera, actually. Okay, so put it in. Okay. And there we go. So the contact in there is not that good. But as you can see, every 1 second, our flashlight's flashing. So it's working. So given this lab signal, okay, lab simulation, this contraption is working. So in the next video, I'm gonna solder this all up, cut back the resistor leads, make them really compact, and I'm going to try to shove the whole contraption here into this case, into the case of the flashlight, because there's a lot of space left in there. And I'm sure if I trim down these resistors leads and I trim down everything, I can solder it and put it right into the whole case without needing a bigger case. So stay tuned for the next video. It's going to be exciting because after we solder this, we're going to test it on a real ABS sensor. So in closing, I hope we've learned something, all learned something on this video um, about how to build tools and test them with microcontrollers. Maybe you haven't seen a microcontroller before or work with them, but I hope this gives you a good introduction to them. They're not hard to use. They're very easy to pick up. You certainly don't need a computer degree to to basically use one of these things. Now, this is a basic usage of it, but as you can imagine, I mean, with all these different inputs and outputs on this microcontroller, the sky is really the limit. In fact, I could have programmed one of these to do the job of the device that we're making. But of course, we wanted to keep this this project a little, low budget, low cost. I also want to challenge myself a little bit to build something using a transistor, and also something with using things that you can commonly find in any store, right? To build something now, and also give me an opportunity to teach you guys about how to adjust resistor values, how to bias transistors, and teach you how about these things work. So it works out in the end. But back to microcontrollers, we could have made a video about how to turn this into an ABS sensor detector. In fact, we could make this and turn it into quite a sophisticated a tester if we wanted to, because this has its own memory. We can track the frequency of the pulses. We can track even the strength of the pulses if we wanted to on this microcontroller. But as a tool, there would be a lot more involved with turning this into something that we can use, because as you imagine, look, this has a USB power supply, right? And it doesn't come with a case or anything that we can put it in. So the packaging is the main problem here, right? So creating a simple circuit like this one, where we can fit everything into an existing case, is a huge advantage for a tool, right? A tool's also got to be in the environment that it works in. This is automotive stuff. Should be pretty durable and tough as well, right? Something like this, like a microcontroller, you'd have to make a custom box for it, and that will be way beyond what we can do with low budget. So that's why we chose it to do it this way. Now, if you enjoy this video, please give it a thumbs up, and please consider subscribing. On the next video, hopefully I'll have this all soldered up, and we can go out to the car and actually hook this up to a real ABS sensor and give it a spin and see if we can see the light up. Have a nice day.